What we've seen so far is that if we have a topology, then we will have convergence and continuity. That will depend on the topology. So if you change the topology, you will have a different convergence and a different continuity. Often, we start with the topology and we ask, is this function continuous? In this case, we're going to do the other way around. We're going to start with a function or several functions and wonder if we can make them continuous by changing the topology. So let's start with a collection of functions. X is a topological space. Yi is a collection of topological spaces, indexes with I, and Fi are mappings from X to Yi. So if capital I is the set 1, 2, 3, the functions will be F1, F2, F3. But I could be much larger. It could be an infinite set, or it could be a finite set. Doesn't matter. I have a collection of mappings Fi, and what I would do is try to find a topology that will make these functions Fi continuous. What I'm saying is that we will always manage to do it, because if everything else fails, I can always choose the topology that is the discrete topology. This discrete topology will make everybody continuous. So it's easy. What I'm going to try to do, though, is to try to find the topology that makes all these functions Fi continuous, but with a fewer number of sets. I'm going to try to have not as many sets as the discrete topology where everybody is an open set. I'm going to try to have the coarsest topology that will work. The reason why I want fewer sets is because as often, as you know, if you have fewer open sets, then it will be easier for the sequences to converge. So you don't want too many open sets, which will make the function f's easy to be continuous, but difficult for the sequences to converge. So what I'm saying here is that I will define the initial topology as the coarsest topology that will make all of these functions Fi continuous. I am going to give you an example. And before I do this, let me just give you a notation. And the notation is sigma x Fi I in I. That is the notation for the initial topology on the set X that will make all of these Fi for I in I continuous. Now it's time for the example. Let me choose basically I, which is only with one element. So I have one function, and this function is 0 all the way to 0 included, and 1 from 0 excluded to plus infinity. So this function f, if you do calculus, you know this function f is discontinuous. Actually, that's part of the sentence only. When you're saying f is discontinuous, it's only the first part of the sentence. The second part of the sentence is it is discontinuous for the usual topology of R. But we can find a topology that will make this function f continuous. So let's do that. And before we do that, let me say that we will equip y with the usual topology, and therefore we are looking for a topology on X that will make f continuous with the fewest number of sets. Okay, let's start. Obviously, in the topology, I need the empty set. I also need R, negative infinity plus infinity, in the set. We'll see that later. But at least I need the empty set. So I'll start with the empty set. Then I need the inverse image of open sets that contain 0. And the inverse image of open sets that contain 0, that will be negative infinity, 0. You can actually try to understand why by looking at the inverse image of any set containing 0. You can pause this video if you want for a few seconds or a few minutes and understand why we have to have negative infinity 0. We also have to have the inverse image of any open set containing 1. And you will see that it is 0 plus infinity. Now, I also have to have the union and the intersections of these sets. Well, the unions will give me negative infinity plus infinity. That's the union of these two sets. Negative infinity 0, 0 plus infinity. If I look at these four sets, I have the empty set, I have the whole set R, the unions of sets here are here, the intersections of sets here are here. Well, what I'm saying here is that I meet all the requirements to have a topology. And obviously, I cannot remove any of these sets, otherwise it would not be a topology. So what I have is the coarsest topology that will make F continuous. This is the initial topology of X that will render F continuous. So this is it. I will now give you a proposition that will link the initial topology and sequences. Let's start with a set X and a collection of yi, as we've seen before, as well as a collection of fi's going from x to yi. Let xn be a sequence of x. In the initial topology, I have equivalence between these two statements. Xn converges to x, and, second statement, for all I in capital I, fi of xn converges to fi of x in yi. Let me prove this proposition. Direct statement first. The mapping fi are continuous for the initial topology, by the very definition of what is the initial topology. So because they are continuous functions, and because we proved earlier that if xn converges to L, it means that fi of xn converges to fi of L, because of this, then the direct statement is really easy to prove. That's basically the proof is here. It's not a problem. So there is no point in proving the statement. The statement is obvious. The converse statement needs a bit more work. Let's start with U, a neighborhood of X. And we can suppose that U is a finite intersection of inverse images of VI's, where VI are the neighborhoods of the Fi of X in Yi. Now, there exists an Ni, an integer Ni, such that past this Ni, the Fi of Xn's are in Vi. So for n greater than Ni, for small n greater than Ni, we have Fi of Xn in Vi. Now because we have a finite number of n, because we have a finite number of intersections, we have a finite number of n i's, therefore I can choose the largest one, and I will call it capital N. Now when I pass n, therefore I pass all of the ni's, then xn will be in U. And this concludes the proof.